Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're going to make the formulas for the total sum of squares, explain sum of squares and residual sum of squares, a lot more intuitive and easy for you to digest. So now that you know the intuition and what exactly each of these variations is telling you, the math behind it will also sound a lot less intimidating. So suppose we observe outcomes. So we have a y variable, and the outcomes that we have in our Excel spreadsheet, which would have looked like this. So you've got your y variable, you would have had values y1, y2, y3, until your last observation, yn. Now let's also define the benchmark that we talked about in the previous video. So let's say that we calculate here also y bar. So the mean, and this is the sample mean of y basically. Everything we'll do next will measure the distance exactly like most of the times from this, but in any case, everything will be in terms of distances from something. Let's do the total sum of squares. The total sum of squares is going to be explicitly as a sum, so the difference between your true observed y and this benchmark, the mean that we just had here. So normally we would be, okay, for the first observation, we've got y1, the distance from y, okay? And because we're talking about distance and variances, so variation, everything is going to be squared. Then for the second observation, we're also going to have the distance from the y, and all of that is going to be squared. And we're going to keep doing that for every single item until the very last one, the difference, so the distance from this y bar squared, okay? So as you can see, this is the total sum of the squares. We take each observation, subtract the mean, square it, and add up everything. If we had to use the summation notation, so the sigma, we would have written that as the sum for I that goes from 1 to n, because as you can see here, we're starting y1, y2, so this is on a loop and changing all the time. So we've got yi, the difference from the y bar, and this is a square, so the sum of all of these differences squared. Okay, so this is something, as you can see, can be computed by itself without you having to run a regression for it. In this particular Excel spreadsheet, you could have easily put the y bar the same value everywhere, and then constructed another column where you have y minus y bar, so you'd get a number by doing for each row here the subtraction, and then these numbers, put them on the square, so you'd have everything squared, and ultimately just find the sum of all of the elements in this column. Okay, so no need for a regression yet. Now suppose we run a regression and we obtain the fitted values, which means that in here you could have had a y hat variable stored in your Excel spreadsheet, and you will have y1 hat here, y2 hat here, y3 hat, and so on until your very last y hat n. These are the model's predictions. Now, these model predictions explained mostly by the model that you constructed. So we had the explained sum of residuals. The explained sum of residual measured how far the predicted values were from the mean. So in this case, we're going to have y1 hat minus y bar squared plus y2 hat minus y bar all squared until the very last y hat n minus y bar all squared. Okay. In summation notation with the sigma, we'll write this as the sum for I from 1 to n, because here this is what changes at every element, we're going to have yi minus, with the hat, minus y bar all squared. Okay, so this is again the variation explained by the model. But there was some unexplained variation left, which was stored in the residual. So we have the residual sum of squares left. And for the residual sum of squares, this was like how far the actual values are from what the model predicts. So in this case, we have a difference of your real y1 and the fitted y1 hat squared. So we would do the same thing for the second observation. And we would have y hat n here minus, sorry, y n minus y hat n all squared. In terms of summation notation, now we can see that the I changes for both the true and the fitted value. So we're going to have the loop going from 1 to n, and we have yi minus y hat I all squared. So this is the variation the model fails to explain. For each observation, now you can think that there is a distance from a mean, there is the distance explained by the model, and the distance left in the residual, which is all of these three elements in here. So distance from mean, this is distance explained by model, and then this one left unexplained. When we sum across all of these observations, and we use the formula that we just learned in the previous video, so the explained plus the unexplained give you the total. Now you can write the math as well. So you've got in here the true minus the mean being equal y hat minus y bar squared, and then the unexplained never forget the counters here. So now you finally have also the mathematical interpretation for it. Keep in mind, this is not a coincidence. It comes from how the OLS is constructed. Why this matters? Well, writing the sums explicitly will help you also see what is being compared, what is being squared, what is being summed. Compact formulas, keep in mind, are shortcuts. So you can always memorize them, but understanding will come from expanding them first. So hopefully me expanding those sums for you will have made these three elements, these three sum of squares, more intuitive and easy to remember now that you know the intuition of. I hope this video was helpful, and I'll see you in the next video.